This session we will learn one important concept that is the demodulation of FM waves. So before to discuss this, so already we know that what is the process of demodulation. Demodulation nothing but the reverse process of modulation. So to get back the original message signal, that is the concept of demodulation. So by using the demodulation concept, we have to get the original message signal of FM waves. So to do the process, the demodulation having two types to derive the FM waves. So the demodulation of FM wave have two types. So one is frequency discriminator and second one is phase lock loop. The phase lock loop is nothing but it is a demodulation in the indirect manner. So in this we have to first discuss the frequency discriminator. In this frequency discriminator, the block diagram consists of slope detection, and that slope detection is followed by the envelope detector. That slope detection followed by the envelope detector. So now we have to see this frequency discriminator. So frequency discriminator is a type of demodulator. Then it produces an output voltage linearly dependent on input frequency. So the frequency discriminator is a type of demodulator. So that means it can produce the output voltage. So that is the linearly, and this one is dependent on the input frequency. So frequency discriminator consists of slope detector, that is differentiator. The slope detector will be act as the differentiator, then it will be followed by the envelope detector. So using this slope detecting technique, simple tuned circuits are used. So in this slope detection technique, we have to use a simple tuned circuits. So this tuned slightly above or below resonant frequency for over a limited range. So tuned circuit nothing but it is the tuning process. So the tuning process is working up to the above or below resonant frequency for a limited range. So here observe this block diagram. So the slope detector will be act as a differentiator, that is d by dt. So the input of this differentiator is the frequency modulated signal, that is s of t. So the output of differentiator, that is the envelope detector. So envelope detector will produce the output, that is the envelope. So the output of this envelope is directly proportional to the m of t, that means the baseband signal or message signal. So mathematically we have to see. So the input of the differentiator is an FM signal. So what is the standard form of FM signal is s of t is equals to AC cos of 2 pi fct plus 2 pi kf integral 0 to t m of t dt. So this is the standard form of frequency modulated signal. Then apply the differentiator both sides, that is d by dt of s of t is equals to d by dt of AC cos 2 pi fct plus 2 pi kf integral 0 to t m of tau d tau. So nothing but, so rearranging that equation, so that is minus AC sine of 2 pi fct plus 2 pi kf integral 0 to t m of t dt 2 pi fc plus 2 pi kf into m of t. So that means d by dt of s of t is equals to, so minus AC 2 pi fc plus kf into m of t sine of 2 pi fct plus 2 pi kf integral 0 to t m of tau d tau. So in this equation we have two cases. So the first case represents the envelope, that is 2 pi into fc plus kf into m of t, and the second case represents the frequency modulation. So that means in the above equation the first term is envelope, that is it represents amplitude modulation. The second term represents the frequency modulation. So based on that equation, by observing that equation we have to discuss some important points, that is the s of t is an FM signal with fc less than f naught of tuned circuit. So the circuit diagram of tuned circuit with resonant frequency is shown in figure. So observe this figure. So here we are using the envelope detector with the resonant frequency. So in this tuned circuit, it consists of resistor, inductor, capacitor combination with the L and C having the shunt type. So this tuned circuit having same transfer function. So what is that? So the amplitude response of this tuned circuit is shown in below figure. So this is represented as the amplitude response of that tuned circuit. So these are the characteristics of tuned circuit. So that is here in x-axis we are represented the FC frequency and F0 frequency. So here the instantaneous frequency Fi of t of Fm swinging above or below cutoff frequency, that is Fc. So amplitude ratio of tuned circuit convert frequency variation S of t into amplitude variation resulting in Sc of t. So like this, frequency variation, that means S of t. So from that frequency variation we have to vary the amplitude response. So here is represented as S of t and this one is t. So this is amplitude variation. So extract only the amplitude variation with envelope detector. Product is SD of t, that is the demodulated signal. So that is the demodulated signal like this. In frequency discrimination method using slope detection technique, the technique having two basic problems. So the frequency discrimination technique having two basic problems. So first one is detector response to amplitude variation of input response, and second one is the range of linear shape is quite small. So these are the two problems in the slope detection technique. So to avoid these two problems, we can use a limiter, that limiter followed by a balanced frequency discriminator. So we have to observe this figure. So first we have to use the limiter response. So to overcome the two problems, so we have to use the limiter device. So the output of this limiter is gives to the balanced frequency discrimination, then it is followed by the envelope detector and we get the original baseband signal. So here is the limiter is a nonlinear device. By using this limiter, reducing the amplitude variation. So to use this limiter, we can reduce the amplitude variation. So the balanced frequency discriminator is extending the range of linearity is achieved. So here the functioning of balanced frequency discriminator is to extend the range of linearity. So to extend the range of linearity. So the modified circuit is shown in below figure. So this is the modified tuned circuit. So here we are using the FM wave, that means S of t. So here is the combination of L and C, inductor, capacitor and resistors, and finally we get the baseband signal. So here the dotted lines represents the tuned circuit, that is the positive slope circuit, and here below represents the negative slope circuit. So the output of the tuned circuit and the secondary are envelope detected separately. So the difference of the two envelope detected output would be proportional to m of t. So the instantaneous frequency Fi of t change with the amplitude variation in opposite direction. So the difference of this amplitude variation is in opposite direction. So here the difference of this amplitude variation is known as S curve, that means the frequency to voltage characteristics. So the S curve represents like this. So this is the figure represents the S curve. So amplitude response of upper tuned filter and amplitude response of lower tuned filter and the normalized output voltage. So this is the representation of S curve. The width of frequency response is about 3 dB. So the deviation del f for which the curve is linear and give the satisfactory output. So del f nothing but the frequency deviation del f is equals to 1.5 dB. That means 2 del f is equals to 3 dB. So what are the cases? If del f of input fm is more than 1.5 dB, so the distortion occur due to non-linearity of characteristic. So operation of this detector is limited to small deviation only. So this is about the frequency discrimination method. So to generate the demodulated of FM waves. And one more method, and the second method of this detection of FM waves is phased lock loop. This is the figure represents the phased lock loop. So phased lock loop is nothing but it is a negative feedback system. So observe this block diagram. So mainly it consists of three devices, that is one is multiplier and second one is loop filter and third one is VCO. So now we have to see this phased lock loop. So the PLL is a negative feedback system. It consists of a multiplier, loop filter and VCO. So based on these three components we are connected together. So to based on these three components the PLL have a negative feedback system. So these three components are connected together, so the form of feedback loop as shown in figure. So here assume that when the control voltage V of t is equals to the 0. So here the control voltage, the output of this loop filter is control voltage, so that is V of t is equals to 0. So then VCO is adjusted, so the voltage control oscillator is adjusted so that the following two conditions are satisfied. So what are the two conditionals? First one is the frequency of the VCO is set at unmodulated carrier frequency FC. The frequency of this VCO is set at the unmodulated carrier frequency FC. And the second condition is the VCO output has a 90-degree phase shift with respect to the unmodulated carrier wave. So the voltage controlled oscillator output has a 90 degrees phase shift with respect to the unmodulated carrier wave. Suppose that the input signal is applied to PLL is an FM wave. So that means S of t is equals to AC sine of 2 pi fct plus phi 1 of t, that is we are assuming as equation 1. So here phi 1 of t nothing but 2 pi kf integral 0 to t m of t dt. So we are represented as equation 2. So here AC nothing but the carrier amplitude and Kf nothing but the frequency sensitivity of the frequency modulator. So let the VCO output can be defined. So R of t, so here we are represented as R of t. So R of t is equals to AV into cos of 2 pi fct plus phi 2 of t, that is equation 3. So phi 2 nothing but 2 pi kr integral 0 to t V of t dt. So that is we are represented as equation 4. Let E of t is equals to S of t into R of t. So the multiplier circuit represents the E of t. So the multiplier of one signal is S of t and one more signal is R of t. So the incoming FM wave S of t and VCO output R of t. So the multiplier have consists of two equations. So one is the incoming signal, that is FM wave S of t, we are represented as S of t, and one more that is VCO voltage control oscillator output, that is represented as R of t. So there are applied to the multiplier and producing two components. So the multiplier producing the two components. So one is a high frequency component is Km ACAR sine of 4 pi fct plus phi 1 of t plus phi 2 of t, and second one is a low frequency component, that is Km AC AV sine of phi 1 of t minus phi 2 of t. So that is the multiplier output is R of t into S of t is equals to E of t. So nothing but AV cos of 2 pi fct plus phi 1 of t into AC sine of 2 pi fct plus phi 2 of t. So AC AV by 2. So here is 2 multiplier and 2 with 2 divider. So AC AV by 2 into 2 sin 2 pi fct plus phi 1 of t cos 2 pi fct plus phi 2 of t. So AC AV by 2 So 2 sin A cos B, that means sin of A plus B plus sin of A minus B. So here is ACAB by 2 sin of 2 pi FCT plus phi 1 of t plus 2 pi FCT plus phi 2 of t plus sin of 2 pi FCT plus phi 1 of t minus 2 pi FCT minus phi 2 of t. So rearranging that equation, so we get the resultant equation. So that is ACAB by 2 sin of 4 phi FCT plus phi 1 of t plus phi 2 of t plus sin of phi 1 of t minus phi 2 of t. So nothing but Km ACAV into sin of 4 phi FCT plus phi 1 of t plus phi 2 of t plus sin of phi 1 of t minus phi 2 of t. So here Km represents the multiplier gain measured in volts. So the above equation represents the Km. So Km is equals to multiplier gain measured in volts. So here, so by using that above equation, so that equation have consists of two frequency components. So one is the low frequency component and high frequency component. So to eliminate this high frequency component by using the combination of loop filter and voltage controlled oscillator. So therefore discarding the high frequency component, the input to the loop filter and is given by, so what is the input of this loop filter is the multiplier output, that is E of t. So what is the expression of E of t is, so E of t is equals to Km into ACAV sin of phi E of t. So that is represented as equation 5. So here phi E of t represents phi 1 of t minus phi 2 of t, that is the phase error. So phi 1 of t minus, so already we know that what is the value of phi 2 of t. So phi 2 of t nothing but 2 pi kV integral 0 to t v of t dt. So that is we are represented as equation 6. So the loop filter operates on its input, that is E of t, and the VCO produce the output V of t. So the output of this V of t is V of t is equals to integral minus infinity to infinity E of tau h of t minus tau d tau. So V of t nothing but the voltage controlled oscillator output. So here h of t nothing but the impulse response of loop filter using equation 5 and 7. So already we know that the what is an functioning of impulse response. So the relation between phi 1 of t and phi 2 of t can be obtained as, so d phi e of t by dt is equals to d phi 1 of t by dt, that is represented as 2 pi k naught integral minus infinity to infinity sin of phi e of tau h of t minus tau d tau. This is represented as equation 8. So here k naught represents km kv ac av. So that is we are represented as equation 9. So the equation 8 can be remodeled as shown in figure. So here is represented as the non-linear model of PLL. So the block diagram consists of the multiplier circuits and the differentiator circuits. So this block diagram represents the non-linear model of PLL. So here when the phase error, that is the phi e of t, so first multiplier output that is phi e of t. So here is phi 1 of t and one of the input signal is phi 1 of t and one more input signal is phi 2 of t. So when the phase error, that is phi e of t is 0, the PLL is said to be a phase lock. So phase lock nothing but whenever the multiplier output, that is phi e of t is 0, that means the PLL having phase lock. When the phi e of t is small compared with 1 radian, that may be used the approximation. Sin phi e of tau phi e of t is nearly equal to phi e of t, that is represented as equation 10. So when phi e of t is small compared with 1 radian, then the loop is said to be a near phased lock. So the phi e of t, the output of multiplier, that is the phi e of t, is compared with is very small value, then compared with that radians. So the PLL is said to be, it is the loop is said to be, it is near equal to the phase lock. So the sinusoidal nonlinearity of above figure, it can be represented by the linearized phase lock loop. So the block diagram of this linearized model of PLL is represented like this. So the here is the block diagram represented as the linearized model of PLL. So from equation 8, so what is equation 8? So this is the equation 8. From this equation, so d phi e of t is equals to d phi 1 of t by dt minus 2 pi k naught integral minus infinity to infinity sin phi e of tau h of t minus tau d tau. So rearranging that equation, so we get the resultant equation, that is d by dt phi e of t plus 2 pi k naught is equals to integral minus infinity to infinity phi e of tau h of t minus tau d tau, that is equals to d pi 1 of t by dt. So that is we are represented as equation 11. So transforming above equation into frequency domain and solving for phi e of f, where phi e of f is the Fourier transform of phi e of t. So the time domain functioning converted into the frequency domain. So at that time we are applied the Fourier transform of that time domain function, then it will be converted into the frequency domain. So what is the resultant equation here is j 2 pi f into pi e of f plus 2 pi k naught phi e of f into h of f, that is equals to j 2 pi f into del phi of f. So rearranging that equation, so we get the phi e of f is equals to 1 by 1 plus k naught by j f into h of f, that into pi of f. So phi e of f is equals to 1 by 1 plus L of f into phi of f. So that is we are represented as equation 12. So here L, what is the value of L of f is k naught by j f into h of f, that is we are represented as equation 13. So here L of f nothing but the open loop transfer function of PLL, and V of f nothing but, so V of f represents in terms of phi e of f is given by V of f is equals to k naught by k r h of f phi e of f, that is represented as equation 14. So V of f is equals to j f by k v L of f into phi e of f. So that is equation 15. So substitute equation 12 in equation 15. So what is equation 12? So phi of f is equals to 1 by 1 plus L of f into phi of f, that is equation 12. So that equation 12 substitute in equation 15. So the resultant is V of f is equals to j f by k v L of f into 1 by 1 plus 2 of 2 L of f into phi of f, that is equation 16. So by using L of f is greater than 1, so we get the resultant value, that is V of f is equals to j f by k v L of f into 1 by L of f phi of f. So rearranging that equation, so j f by k v pi of f, that is equation 17. So V of f is equals to 2 pi j f by 2 pi k v into pi of f. So here apply the inverse Fourier transform to the above equation, then we get the time domain function, that is V of t. So V of t is equals to 1 by 2 pi k v d by dt phi of t, that is equation 18. So the above equation can be represented by the following model. So the figure represents the simplified model of PLL when the loop gain L of f is large compared with the unity, compared with the more value. So here by substitute equation 2 in above equation, so we get the value. So V of t is equals to 1 by 2 pi k v d by dt 2 pi k f integral 0 to t m of t dt. So that means, so V of t is equals to Kf by Kv into m of t. So this is the resultant equation. So here we are assumed equation 19. So that is the output of the V of t of the PLL is approximately the same except for the scaling factor Kf by Kv as the original baseband signal, that is m of t. So V of t is directly proportional to the m of t. So this is about the phase lock loop method. So these are the two methods. So we will get the original message signal of the FM waves. Thank you.